Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone, welcome. This is a course on mathematical statistics, so I hope that's what you're here for. There are a number of different course codes. Could you please put your hand up if you want to or think you're in Principles of Mathematical Statistics, which is Math 6039. Can I just see how many, roughly? Decent number. There would also be one that's called Principles of Mathematical Statistics for Actuaries or something along those lines, 6013. Can you put your hand up if you're in that? Also a decent number. Is anyone in STAT6013, Introductory Mathematical Statistics for Actuaries? Can you put your hand up if you think you're in STAT6013? One person. That's interesting because I was told that this is a code that generically exists but doesn't exist this semester. So if you're in that one, that's interesting. I'll chase that down. But in any case, it has the same course content. So you see this is a parallel undergraduate and postgraduate on one end of the matrix, and also for actuaries and without on the other end of the matrix. In case you're wondering about the differences, between undergraduate and postgraduate, there is effectively no difference now, apart from the title and the course code. There used to be an extra section on regression for postgraduate, but that's no longer included in the course. There are better courses on regression, including STAT6008 and many things in the third year part of statistics, so we no longer have just a very quick introduction to regression here. Having said that, and the final course code, so that you don't feel left out, is in some sense the primary one, which is STAT2001, Introductory Mathematical Statistics. Could you please put your hand up if that's what you're here for? Okay, once again, a decent number. It's probably a fair balance among the three that we have, 2001, 6039, 6013. And for the actuaries, the 6013 course, there will be some extra lectures, which I think have been scheduled on a Tuesday, but that's the only otherwise difference relating to that course, to ensure that you fulfill all the requirements of the actuarial training. So, welcome. Whether it's called Introductory Mathematical Statistics or Principles of Mathematical Statistics, we will be covering essentially the same thing. So I've printed out, by the way, the course outline for Introductory Mathematical Statistics, STAT2001. You probably, this is a way for me to see whether this scanner is working very well. I guess the moral of the story is don't use small writing. This is straight off the website, Programs and Courses. So if you've been here for, if you've been at the ANU since 2018 or earlier, you would remember that everything used to be done with our own course outlines. Now it goes through a big meat wringer onto the official website. So this is now the official course outline. It's also called a class summary. There's no more official version that I can give you other than what's on the Programs and Courses website. To get it, you have to find a little view button. It's not very well outlined. But tell me if you have trouble finding that. In any case, it should be linked from the course Wattle website. The Wattle website I'll assume you all have access to. You must tell me if you don't, because that's where everything will be posted. There will be a tutorial in every week except for the first week, so no tutorials this week, but second week and onwards, starting on Monday, depending on which. Some of them are on Monday, some of them are later in the week. Each tutorial will cover the material that we've learned in the lectures the previous week, which is 3 lectures a week. Monday at 2, Thursday at 9, and Friday at 3, if I remember rightly. The official source of that is the timetable website, but you all found your way here, so I think you all will have done that correctly. I could read through the learning outcomes themselves and so on, but I won't do that so much. That's an official course registered with the university, and those things don't change from year to year effectively. So there will be some changes of emphasis and some small variations in the lecture material, but overall this is the standard course, same material as if you would take this in first semester with a different lecturer. But I taught this course in second semester last year, and I'm also teaching it second semester this year. It says a number of things that you'll learn to do, but in essence what is going on in this course is that mathematical statistics means that we're learning to use statistics in a more sophisticated way than simply as a set of methods or techniques that you don't need to inquire into. There will be more emphasis on the mathematical background, and there will be more emphasis on the justification. So that means we will cover some proofs of facts that in your first statistical course would have been asserted. We won't necessarily prove 100% everything, but you'll have a fundamental understanding of how it works, and you'll also understand how to vary the methods because of that. So, having mentioned your first statistics course, can I just ask you to put your hand up if you have taken a statistics course before? Not this one. Okay, so I'm hoping that's pretty much 100%. It looks like high 90s at least. And that is correct, because although the name of this course is Mathematical Statistics, it assumes you already know some statistics. Not actually for the mathematics. The mathematics doesn't depend on that. But the reality is in this course we'll not be training you in a lot of basic methods. We won't be saying, oh, this is how to do a t-test, this is how to do a regression. And in fact, part of the reason that regression was removed from this course for the postgraduates is that you would have already taken it in a basic statistics course for simple linear regression, which is where you have a set of y values and a set of x values, real numbers, and you just fit the least squares line and do some inference that way. So that was covered at a basic level, and at a more advanced level there are many other courses in the STAT department. So it's no longer covered in this course, regression. But what is covered is all the mathematical statistics that you need to understand how those methods are put together. And so in terms of mathematical statistics, what are we getting at there? Well, the main tool is probability theory. It's not the only tool. So while I mentioned that you will have already done, at least as an undergraduate, they probably have enforced the requirement that you've already done a statistics course. As a postgraduate, that may have been listed as recommended knowledge, but still we'll assume you don't need basic instruction what the methods are trying to achieve, what kind of tests. So STAT1003, or I'll just say that is the kind of assumed knowledge on the statistics front for this course. There's also mathematical assumed knowledge. So while this is mathematical statistics, we're not teaching you the mathematics basis that you need to start. So that's also assumed knowledge and also a prerequisite in a number of ways. So I think 1113 is one of the course codes. So it would be a number of other course codes that express. So, by the way, this probably isn't showing super precisely what is going on, so I'll make that in mode. And what are the key features of math? If you haven't taken that exact course, you might have transferred, you might be a postgraduate student and not required to have it. The key things that we'll be using from that are calculus, which includes differential and integral calculus. Okay. But often covered in a calculus course, and also very important, is the theory of series. Just how to add up infinitely many numbers, possibly. Tell whether they do converge to a solution or not converge to a solution. And that will be important because often the most basic operation that you do in probability theory is taking an expected value. This is the theoretical analogy to a mean. You would have already heard about an expected value. But in the case where you have a finite number of possible values, you just add up the values times the probability of those values. In the case of infinitely many values, you have to add up, once again, an infinite number of values times the probability. So that's where series comes into it. You have to be able to look at series, not necessarily answer every question about them, but know that there's a possibility they converge, a possibility they diverge, which means it doesn't converge, and also some methods for evaluating the sum when it does exist. And sometimes they will be power series, sometimes other sorts of series. When it comes to differential and integral calculus, once again, that I talked about the case of discrete random variables. In your first statistics course, you should have heard about discrete and continuous random variables. Just discrete random variables have a list of possible values they can take. Not necessarily finite, but a list. So like 1, 2, 3, 4, 5, often. For a geometric random variable, which you probably have heard about, the possible values are 1, 2, 3, 4, 5, any positive number. It could be any list of values. But quite different from those are continuous random variables, which take a whole uncountable continuum of the possible values. So series are useful for when you have, I guess, a discrete random variable, which is sort of like the probability mass function for a cartoon would be, there's a certain massive probability at each possible point. And differential and integral calculus comes into the play when you're dealing with continuous random variables. The most famous continuous random variable, can someone tell me the name? Normal random variable. Sometimes called a Gaussian random variable. Normal and Gaussian in this course, and in fact in all of probability, are synonymous words. So arguably Gaussian would be a better choice of name, because normal is such a common word in the English language that you can forget that it means this very, very specific distribution. It can have any centre, it can have any spread, but that's what the word normal means. Gaussian is synonymous, but I guess mostly I use the word normal. So that's why you need those parts of mathematics. And having said that these were the two prerequisites if you're an undergrad and the two recommended materials if you're a graduate student, in reality the mathematics is more important for being able to keep up with this course. The statistics is sort of background because it'll tell you what we are aiming at, but even if you don't know what we're aiming at, you'll still be able to learn the probability theory in this course. So I've said that the name of the course is Introductory Mathematical Statistics, and indeed the last 3 weeks, 2 or 3 weeks, will focus a lot on statistical applications, how to do tests, and the theory behind testing and estimation. But if you look at these first 4 learning outcomes, use and calculate probability, including combinatorics, use and describe discrete, continuous and multivariate random variables and their probability distributions, describe sampling distributions, and use the central limit theorem. Okay, the first 3 learning outcomes are all probability theory, not statistics at all, but it's something you need to understand in order to do statistics. And then the last 3 outcomes are genuine statistics, so that they will be applications of the probability theory. In order to do that, we have to get into the probability theory itself. So I'll let you read the whole course outline yourself. There's a lot of kind of unimportant material, a lot of important material that's there. The unimportant material is mostly a compulsory field, so you can try and concentrate on the things that are most important. The class schedule is somewhat important, and you'll see that it gets... by the way, there's a chapter that this is referring to, and it refers to the following book. I would do this, but I'm aware that this is probably a more reliable way for anyone who watches the video catch-up to see it. So this is the textbook, Wackley, Mendenhall and Schaefer. You will be assumed to have access to this book. It's very central to the course. We'll be covering the first 10 chapters over 12 weeks, plus a little material on Bayesian statistics. And the first 10, and it also, it should be available at the bookshop, including a companion book which is by Owen, maybe Owen and Mendenhall, called The Solutions to the Problems. That's there because you may well want to do a whole lot of exercises from the book by yourself to practice, and then the solutions will help you to mark those. But certainly the book is essential. It's also on reserve in the library, Hancock Library, which is the science one, and you can just go into the 2-hour loan and there should be at least 6 copies, I believe. Some of them may be taken at any time. So you shouldn't have any trouble getting your hands on the textbook. If there's any problems with the textbook, email me, but you shouldn't have any problems. So that's what the chapters are referring to. As often with these books, Chapter 1 is a bit of a cop-out. What is statistics? So we pass over that very, very quickly because there's no real point doing a lot of statistics until we have the probability theory to to encompass that. Now, it says quiz. You'll note that's not it's a quiz that is worth 0%. So this quiz is there to give you some feedback about how you're travelling, but it does not contribute to your final mark. That'll be on the Wattle website, and you can, I guess because it doesn't contribute to your final mark, the answers will also appear on the website so that after you've done the quiz you can mark your own work. That's the way to get feedback. And also the tutor will be very happy to give you feedback on that, and I also myself will be happy to give you feedback. Did I mention the office hours on this? I think you have to click through a number of tabs on the new class summary website to see my office hours, but because that might not be clear, I will state it here. Did I already take that off? Anyway, each individual tutor will have their own ability to do consultation times, but finally, so for mine it is 10 till 11 a.m. on Thursday. That's I'll keep that constant the whole of the semester. There may be sporadic extra consultation times if you need to see me. So the CBE building is where my office is, office 346. You should feel free to meet me or come to my office at that time, any time during the semester for anything whatsoever. Often people find themselves finding it awkward to talk to the lecturer. If you don't want to, you don't have to, but feel free to ask absolutely anything. That's the best time. Otherwise, you can email me to try and talk some other time. I'll be available just with my door open for anything you like at that point. Now, you can also ask your tutor for anything you don't want to ask me. The tutors will certainly be involved in the marking of the 2 assignments and the exams. It won't all be done by me. And there may be other graders as well. There is an assignment 1 that's due in week 6, Tuesday of week 6, and there's an assignment 2 Assignment 2 is due on Tuesday of week 10. You should treat those as hard deadlines, not expect to get an extension or anything, because they won't necessarily be granted unless there's a good reason. So treat those as hard deadlines. Tuesday of week 6, Tuesday of week 10, all of that is in the course outline on the website. And those will be posted at least 2 weeks in advance. The mid-semester exam also exists. That has to be scheduled remotely, and I don't get to decide when that is. Could be week 6, could be week 7, which is a wide range because the mid-semester break is between week 6 and 7. So stay tuned for when the mid-semester exam will be. It'll cover everything up to that point pretty obviously. And the final exam is at the end of the course. That will cover absolutely everything, including the first half. So I think that's all the administrative things I wanted to say. Were there any other questions about the general setup of the course? Assignments, tutorials. By the way, to get in the tutorial, you have to enrol online on the Wattle site. If you haven't done that already, pick one on the website. If they all become full, it's possible that new tutorials will be open, but I don't think they have become full. So at the moment, you should just enrol in one of those tutorials. Once again, email me if there's any problems. Okay. I didn't introduce myself at the start of the semester. My name is Lawrence Field. I'm a lecturer in the School of Statistics, which is part of a larger school, the Research School of Finance, Actuarial Studies and Statistics. And I know that there will be some actuarial students among you, although I'm not a specialist in actuarial studies. I am a specialist in probability theory, which is the main thing that we're doing, and then some applications to statistics thereafter. So my own personal research interests are in stochastic processes, Brownian motions, and various spatial processes, geometric processes, and those are really higher level versions of the probability theory that you'll be learning the basics of in this course. In case anyone has the mathematical background and knows about measure theory, you don't have to know about measure theory, and in fact this is a non-measure theoretic course. So measure theory, for those who don't know, is the underlying theory of the most sophisticated integration that is used in higher level mathematics. It's called Lebesgue integration theory, and more generally it's called measure theory. Now, that's not necessary for the most simple applications that we do, and so it's not assumed at all. But what it means is this is a non-measure theoretic course in probability. It is not fully sophisticated enough to construct things such as Brownian motion, which is something that is covered in third year probability courses, including stochastic modelling. So while that sounds disappointing that it wouldn't cover everything you ever need to do with probability, I'll say this. what we cover is just a subset of what you need to know. Nothing is incorrect, it's just we don't cover the sort of obscure corner cases and difficulties that happen when you want to be fully comprehensive. So while it's a non-measure theoretic course, we still cover everything you need to know to cover discrete and continuous random variables, and also multivariate random variables, which is something we'll be covering in chapter 5 of the book, probably week 6 of the lecture course. I believe I've now said everything that I want to say about what will be covered in the course, and we can get on to actual content now. But before I do so, are there any questions about the structure of the course, or assessments, or tutorials, anything of that sort? No? Good. Well, thanks for your attention on that. Now I have a kind of a process question, which is that... I'll worry about that later. So let's get straight onto the notes. I'm going to... not laptop. Okay, so this should be showing me some slides for the moment. I won't always be using slides, but sometimes I will. And as I said, the first, the introduction to the course, which is at least part of this week, and it's chapter 1 in the textbook, it is the general introduction, which once again is light in content. There's a little bit of review of characterizing measurements, characterizing data without statistical techniques. But I really want to touch over this very lightly. If you look at your textbook, if you have it, you can look at it later. Chapter 1.2 is, 1.1 is talking about really the history of statistics and why we're using it, and why we need mathematical statistics and probability theory to underpin that. So that's just telling you what we're doing and why. Because there is some sophisticated mathematics in the probability that we have to do, I want to get onto that as quickly as possible. So I'll let you read the full introduction as much as you like, but in essence, statistics is the science of learning from data. So while that is conventionally broken into inferential statistics and descriptive statistics, the descriptive statistics part of that, which is, as it sounds, just describing a set of data, is a bit of a dead end. And I shouldn't say that, because you can get very, high-paid jobs for, newspapers these days and other things very much like graphical data presentation and finding new ways to find meaning of data in that sense. And while it's a very important thing to do, especially for the understanding of the data sets you come up with, it's not the focus of mathematical statistics. So that's why we cover it over very well. But summarizing numbers graphically and numerically. And let's think about why it's not considered the be-all and end-all of this course. If I take the statistics that, as it's been developed, and certainly for this course, was forged in an era of limited data, where you have to be very careful, and that's still the case in many, many contexts. Any case where data is expensive to gather, you can't be really sure of its validity, and to make it more, for instance, to gather data in a particularly fair manner can cost more, because you have to ensure you have a truly random sample, ensure independence of all the inputs that you might be trying to talk about. All that costs money. So if you're trying to have really good data, you might also have really limited amounts of data. And if that's trying to make inferences about large populations, whether it's, the population of a country like Australia, or whether that's a population of experiments. You can consider experiments as a virtual population, because if I just repeat the same experiment under the same conditions, there'll be a random distribution of results. That random distribution can be considered a virtual population, and just doing a few experiments is sampling from that virtual population. In either case, there's much more information in the true population than you're able to get from a few sample points because of the expense. And so the science of statistics is about upgrading the information you have about your flawed sample that was just, after all, random, upgrading that to the whole population. And so while descriptive statistics, which is this chapter 1, might talk about summarizing a set of numbers, finding its mean, finding its median, in reality, if I've sampled 100 people from the population, and let's say it's the best possible sample, which is an independent sample where everyone is equally likely, that's a independent, simple, random sample, just the fact that a certain number is the average among that sample doesn't mean it'll be exactly the same among the general population. Far from it. What you can say is that the sample mean is likely to be close to the true mean as the sample gets larger. And even for a small sample, you can say something about the likely size of the error. And to quantify those things, we have to use probability theory. So while it's nice to summarize your sample's not the same as the population you care about, so the connection is what's most important. So let me just skip. Okay, so that's the introduction. There are a few examples from each chapter of the book, which I'm actually not going to cover right now. By the way, these slides come from a set of notes, which is, they're not original to this year, so there will be some slight changes in the lecture material this year. But nevertheless, I will post this original set of notes for STAT6039 on the website. There's already chapter 1 and 2 should be up on the website. And you can use that as a basis for learning. I want to emphasize that the true yardstick of what's covered in the course is what I cover in lectures. It's not the set of lecture notes. Because there might be some things in the lecture notes that I think we don't need to cover. They're not critical to the learning outcomes and we won't cover. So your 100% guide to what's covered in the course is what I say in lectures, not the notes. Nevertheless, they will be posted. So I'm just going to skip over this preview of some of the problems from each book: probability, discrete random variables, continuous random variables, multivariate probability distributions, which you can also talk about multivariate random variables, functions of random variables, sampling distributions and central limit theorem, point estimation and confidence intervals, methods of estimation, and hypothesis testing. Now, one of the key things is, compared to these notes, is we'll also have some material on Bayesian inference. So stay tuned for that towards the end of the course. Getting back to this introduction, chapter 1. So, as I said, statistics has descriptive part and an inferential part. And the descriptive part, as I said, is sort of the baby part. And it's still important. It's still important to present your data. But arguably, it's well known that there's kind of a lack of statistical literacy often in public presentation of research, and sometimes this is exploited, unfortunately, that the true uncertainties in data are not reflected. For instance, it's extremely common in social research to say such and such a percentage of the population was found to support X measure, or indeed, opinion polls, anything like that. Even the most basic thing which you would have heard about, which is the margin of error, is often not presented in those. The margin of error is the first level of inferential statistics because it tells you what is the typical amount by which a deviation is... okay, so they might say, sometimes they even say something like maximum margin of error. Say I have an opinion poll, do you support measure X, which might be a proposed law. And they say that 48% of the population supports the proposed law, and sometimes the newspaper might quote a maximum margin of error of 3%. Does anyone want to say something about this maximum margin of error? Because often that's the word used, not just margin of error, but maximum margin of error. Is it fair? So say, to be specific, say they try to sample the Australian population, everyone has an equal chance of being chosen, and say they say that from this sample, which maybe they had 1,000 would be a large sample, or 10,000 would be a very large sample, but nevertheless 10,000 is still a tiny fraction of the Australian population, less than 1 in 1,000 of the actual population. So would it be fair to say maximum margin of error is 3%? What would that be claiming? That it's impossible that the true value is more than 51% or less than 45%. Do you think that's correct? Just to be clear about, I'm being a little bit interactive, I'll just go back to try and write something about what I'm talking about here. I have, okay. To be very concrete, we have the Australian population, which is roughly 25 million at the moment. And let's say we have a very large sample by social work, social research standards, which would be 10,000. Okay, so very large, but still pretty small fraction of this thing. Okay, so what we find reported was that, support a proposed law X, it doesn't matter what it is, we're just talking about a yes or no question. Yes or no questions are the simplest ones, and it's reported that 48% support, maximum margin of error 3%. Now, I also hope that this is something that was at least touched on in your first statistics course, how you might do such a sample and what would be the method of analysing it. Thinking back to your first statistics course, certainly the undergrads among you would have done that recently, I hope, or at some point. And okay, we're not doing a hypothesis test. We're just doing an estimate, so a confidence interval. Really, this is suggesting a kind of confidence interval from 45% to 51%. I think that's what it's meaning to suggest. So, is it fair to call that a maximum margin of error of 3%? Someone? Please put your hand up if you want to answer, or indeed just speak out loud. I'm trying to make it a little interactive to see where everyone is up to. I feel like I'm harping on over one word, but I want someone to criticise it a little bit, because I personally would criticise it. Yeah?
I would change to 3% because it's not the 3% of 48%.
Yeah.
3% of point.
Yes. Okay. So that would be one criticism you could make. Yeah. So sometimes they say PC. Or let's write it out in. I see what you mean. Percentage points, because often when you write the percent symbol, you mean percent of the last figure. So it certainly doesn't mean 3% of the 48. It means 3 percentage points total, going down to 45 and 51. That would be one critique, but it's not the only critique. Anyone else? Yep.
The margin of error is usually given with a confidence interval. So if it's outside of that confidence interval, say 95%, then 5% of the time that margin of error will not capture the true number.
Exactly. So yeah, so that gets to this word maximum, doesn't it? Is it really a maximum? Can you try and salvage the word maximum? Like, what does it really mean by saying it's maximum? You could say it's maximum at that confidence level that you referred to, right? It's, which is not a maximum at all, but it's, except for very rare events, it would never be more than 3% out, except quite rarely, by which we say 5%. So all of a sudden this starts being a little less convincing. But to be perfectly blunt, there's no way you can say it's absolutely impossible to have more, outside that confidence interval. So often this would be a 95% confidence interval, although, there would be a 99% confidence interval that's a little wider. But it is possible to be outside that confidence interval. To perfectly blunt, there's half the country thinks yes, half the country thinks no. It would be easily possible, especially if you had a biased way of sampling. So, you see, you're trusting the person who said the survey to say, oh no, I did everything in a perfectly unbiased, independent fashion, everyone had the same chance of being chosen. Now, in reality, that's hard to achieve even if you do want it. And then, a lot of research is done by motivated reasoning, people with motivated, if you're on a contract for a certain side, even if you don't deliberately want to give a totally fake poll, if you have an incentive to produce a result that is more towards one side or other, that can lead to a sampling procedure that is not fully unbiased, that is not fully equal chance of sampling every single person. So with commissioned polls, with research that is done for payment for a certain person, there is often biases, either unacknowledged or acknowledged, that come to the surface and can cause that to be unvalid. But even if it is valid, even if everyone is equally likely to be chosen, it's possible, it's just less than 5% of the time, that you will get, most of them among the other side. It's possible that you would get 55% support the law, just if you happen to be, by chance, sampling more towards the supporting part of the population. So the maximum margin of error is, that maximum is only at that confidence level. So that would be my critique of the word maximum. So part of what you're learning to do in a mathematical statistics course is to provide such critiques of any kind of statistical reasoning, whether it's in papers from other fields. So as we know, throughout economic research, throughout social research, there will be statistical analyses done of surveys, and you've really got to have your tendrils up for possible flaws of the analysis. And they come in a whole way, as you saw, they come in a whole range of possibilities. One which is just that you could be unlucky and have a bad sample. 95% confident sounds confident, but it's not that confident. 1 in 20 times you'll get something outside that confidence interval just by chance. And not only that, but there are also the biases that lead to even worse misinterpretations. So we have to be aware of both of those. So I'm going to go back to the slides, and we're still doing the summary of what will be covered in the course. Tables, graphs, averages, and simple summaries. I want to cover that today if possible, but I've spent most of my time so far denigrating it. So it's something that's worth knowing about how to do, but it's by far from the end. So in some sense, in the example we just talked about, the descriptive statistic really is 48%. It's just a number. Like that would be the proportion. When you're sampling for proportion, there's not much to describe. Very little, just a number. When you're sampling for one reading from each sample subject, so for instance, you could sample people and measure their height or measure a certain continuous variable. Then you have a whole lot more data, and it does start to be complicated to summarize it. You don't want to just list out all the data points. And so there are various tables and graphs. Sampling people from Canberra and measuring their height is the example on this slide. And you could estimate the average height, but all of a sudden, because you have the actual data points, not just yes or no, you can start thinking about what is the actual shape of the data. Now, there's an easy assumption that is, okay, let's think about this example, sampling heights for people from Canberra. There's an easy assumption that is very common to make and maybe should be queried, but is sometimes a good assumption. What would the easy assumption to make about the height of Canberrans be? The shape of it. Yeah, very easy assumption to make that it's normal. And it's almost like a fish. If you do too many statistics courses, there's a form of mental reductionism or mental cramping that can occur whereby you think that everything is normal. And I just have to tell you it's not the case. So having said that, height, at least if you restrict to a fixed population, probably say adults only and let's say one sex, because there is a statistically detectable difference between the average height of women and men. But if we stick to one sex in one population, we probably would see a roughly normal distribution. And it's interesting to wonder why that happens. We can get into that more when you start talking about the central limit theorem, but the potted summary is there's a reason the normal distribution is easy to just think is ubiquitous, because it comes up surprisingly often. And it comes up particularly when there's a whole lot of random influences which are pretty independent of one another and none of them swamps the others. So if I had like one huge fish in a pond and 100 small fish, then the average weight of the fish wouldn't necessarily be normal because it would be determined entirely by the big fish. But if you have 100 fish in the pond, all of which are about the same size and pretty independent of one another, then the average, the distribution of the average weight would be roughly normal. So it's an averaging effect that causes. So that's my two-word potted summary of the central limit theorem: averaging effect of independent measurements roughly the same size. Of course, there's a much more precise statement of the central limit theorem that we'll say lately. So that's why the central limit theorem, the normal distribution, this bell curve, comes up very, very often, much more than you'd expect naively. But it's not everything. As soon as you don't have those conditions, you don't have necessarily a normal distribution. A lot of things are bimodal. You can encode the answer to the question, do you support law X, as 0 or 1, 0 for no, 1 for yes. Often that's a useful thing to do. We even call it an indicator function, but I'll get to that later. But if you just encode things as 0, 1, that's not normal. It only takes 2 possible values. And most discrete things are, clearly the normal distribution is a continuous distribution. We'll get to that later. Discrete distributions are not continuous, although they can look like it. But a discrete distribution that has either only values 0 or 1 is definitely not even close to normal. So many things are not normal, and we've got to step back from the fishbowl of inferential statistics to just not automatically assume that everything is normal. Okay. Nevertheless, under that assumption, we can make some really good conclusions. So if it's a good assumption to make, then we're in a very good situation. We've talked descriptive stats talk a bit about in chapter 1, but the basic summaries you'd want to talk about are the histogram. By the way, even from a histogram, we'll get to that in a moment, you can tell whether something's roughly normal shaped. So that's a good good reason to look at it. You can also look at, there's density plots which are hard to do without a computer, and they're also approximations, so I don't recommend those. And we'll talk about some other methods, just summary statistics. 2 through 7 are probability. So all of these little charts are in the lecture notes. I'll let you look at it a bit. We need to know some maths. Calculus, as I said, is assumed knowledge. So that I can't, if you don't know calculus already, I can't teach it to you. I hope you have a good textbook on the side or a crib book to help you understand the series and integrals and differentiation. Set theory, maybe you haven't done so much, I'll still have a quick reminder. It's quite easy once you get the hang of it. Just some notation, really. And then probability, we set up using calculus and set theory. That's the most standard way of doing it mathematically. And then that'll feed into inferential stats. So you can do some estimation, you can do some hypothesis testing, and once again, it's something missing from this chart, Bayesian inference, which, if you don't know what Bayesian is, well, you've probably heard of Bayes' rule. You did first year statistics. Bayes' rule says, how do I know the unconditional probability of something happening, but then I'm given new information, like, you know, I know if I just pick a random day, what's the chance that it's raining in Canberra? Pretty low. But then I get new information. I look out the window and I see a storm cloud. All of a sudden, it's not so fair to say it's still very low chance of raining, because with that information, I can use the conditional probability. It would now be higher. I see a dark cloud. The conditional probability that it'll rain is a little higher. Bayes' rule, as you would remember from your first statistics course, tells you exactly the formula for how to update it. Effectively, it's a ratio of conditional probabilities is how you update the formula. Now, so what is Bayesian statistics? How does a simple formula or a theorem that's always true become a somewhat controversial attitude? Well, the reason is Bayesian statistics is effectively subjective statistics. Rather than having some once-for-all declaration that I think this happened or I think this didn't, based on some arbitrary cutoff of 95% confidence, which is the same as a 5% significance level, Bayesian statistics says, well, you'll have to convince me. You know, how much information do you have? I have a prior belief, how likely I think it's likely to happen, and then you can tell me some more observations that you made. Each of those observations updates my conditional probability by Bayes' rule. And the Bayesian viewpoint is that, well, I might set some personal threshold for how confident I want to be that something is true, and by updating using Bayes' rule, I can wait until it gets to convince me that it's true. Someone else might have a different prior, and they might require more or less evidence to convince them that it's true. It sounds very unsatisfactory because it's subjective. In fact, it's not unsatisfactory at all, because it turns out, regardless of where you start from in belief, so long as you don't rule something out as totally impossible, that you'll just need a little bit more evidence to convince. Some people might be easier to convince than others. So it's a very sophisticated part of statistics of increasing importance nowadays. All the spam filters and any kind of predictive, fraud detection online is done using a Bayesian method, not just frequentist method. So these days, it's really important to know about, and the subjectivity, you get used to it. It's an important thing. So, having said that, that's right at the end of the course. So something to look forward to. Descriptive statistics. I have only a little amount of time to do this. So 10 values. By the way, these subscripts, of course, are just a way of indexing. Often a sample's done in no particular order, but there's no harm in recording the order it was done. I is just the index. Index means which order was it done? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this was a sample that was taken, or profit on a particular day. How can you summarise them? Well, if you just want to mix them all up, you don't care about the order, a good way to do it is a histogram. So histograms have bins, and the bins should lie next to each other. You're literally chopping up the real number line, just all possible numbers, into a number of bins. Now, the choice of which bins depends a lot on the sample. If it's a small sample, maybe only 4 or 5 bins. If it's a large sample, maybe 10 or 20. And I think these notes say that you should always have 5 to 20 bins. Well, that's not really true. If you had a sample of size 10,000, which is rare, it's a very large sample, then you might well have 100 bins. So it's to do with how large the sample is. But having too many bins can imply false confidence. So as you see, the bins just start at a certain point, end at a certain point. We typically try to have the bins of the same width, because if they're not the same width, there can be difficulties in in interpretation, especially if you have a frequency histogram. So all of these are frequency histograms, which frequency is used as the y-axis, and despite the name frequency, it sounds like that should be the proportion of times that something happens. Unfortunately, it sounds like it. Unfortunately, to statisticians, the word frequency is identical to the word count. So a frequency is a count. It's how many times does it happen. So you see it's always 1, 2, 3. It's always a whole number. So if you want to say what I think would be a better meaning, the relative frequency, which is as a proportion of the total, how often does it happen? So if you have a sample of size n, and it happens k times, then k out of n is the relative frequency. It's just a proportion. It's between 0 and 1. So the relative frequency histogram is a more useful thing to have, especially if you do it relative frequency per x value. I don't want to get into that at the moment because it's really unimportant. But so just remember that a frequency histogram will have, in each bin, the y-axis will just tell you the count. Now, if all the bins are the same width, which is important, then a frequency histogram will give you a good idea of the shape of the data. If the bins are not all the same width, why is that a problem? Because, if I just amalgamated these two bins all into one bin, if I did a frequency histogram, suddenly there'd be two things in this mega bin rather than one. So if the bins are not the same size, then you can just arbitrarily make it go higher, so the shape would change. So that's clearly stupid. So for frequency histograms, which are, after all, the most common type, if you do it in R, then you'll get a frequency histogram. It's really best to have all the bins the same width. Now, as to where the cutoffs are, it's a little bit arbitrary. If you do it in the R package, which many of you will have used in STAT1003 or 1008, or any other package, it'll just pick them for you, and you can override that. There's also a little question which is alluded to here. What if I have something that lies exactly on the end of the bin? Maybe it's 2.25 as the end of the bin. What if I have something that's exactly 2.25? Well, you just have to make a choice. Either all the left endpoints are included in the bin to the right, or all the right endpoints are included in the bin to the left. You just make a choice. I think it's usually all the left endpoints are just by default. Once again, in the R package, it's by default one way or the other. So that's really not going to concern us in this course, but it is a choice that has to be made. So that's what this slide is about. You can read about that as nauseum if you like, but I'd really de-emphasize it. So really it's the number of bins that's most important. You'll just get slight issues from where the exact cutoffs are. In other words, the histogram won't always look exactly the same. But if the data set has 20 or 30 or more, then just looking at the histogram with an appropriate number of points is a good way to see the overall shape. You could guess, yes, it looks roughly normal, or no, it doesn't look roughly normal. That's what we'll be interested in most frequently. Okay, R code is non-accessible. I should have said this at the start. The R package is a very popular free open source statistical package. I highly recommend it. If you took my 1003 course, I see a couple of faces that I did, then you'll know a lot about how to do that, or in another course you may have learnt. Now, it's really not an emphasis of this class. There is no computer assessment. There'll be no computer involvement for the assignments. So while there's some R code in these lectures, you can ignore it if you like. You can use it as just a fun way to test your understanding if you want to play around on the computer that way. So it's not emphasized in this course. So numeric summaries are more important. Arithmetic mean, you all know about it. You add up and divide by n. And so there's a population mean which is not directly observable from the sample. And the biggest, so that's just if you treated the whole population of, say, 25 million Australians as one big sample, which you can't actually sample that many, but sometimes you do try to touch them all. The census, plus or minus some errors, will measure everyone, and then you can get a population measurement. Now, the sample and the population are not the same, and the whole point of inferential statistics is to quantify the difference. Sample variance. The key thing to know about sample variance, it is the average squared deviation from the sample mean, but that average has an asterisk. The asterisk is you divide by n minus 1, not by n. For a good reason, it makes it an unbiased estimator of the true variance, but for now, just remember you always divide by n minus 1. That's the same as we did in first year. That's the standard on all packages, I'm pretty sure. So it's in squared units, so if you want something that's in, so you don't want to measure it measures the variability. How far on average are you away from the mean? It's squared, so you don't want to say, 57,000 squared dollars. So you just take the square root, and that's called the standard deviation. Once again, this is the sample standard deviation. There's a true one that we'll talk about in the probability theory. Now, the empirical rule, these notes over-egg the pudding. They say this happens 68% in one standard deviation, 95% in two, and 99.7% in three. That's true for a normal distribution. If it's not normal, then this is not guaranteed. The most you have is some bounds, which are given by Chebyshev's inequality. We'll do that in the probability theory part. So you have some bounds